Hello, I am Sriram. My roll number is 24951A6747. I am from CSC Data Science Department, and this course title is Operating Systems. Course code is ACS D09, and here the topic title is Building a Log Structured File System for High Performance. Building a log structured file system for high performance. It's all about revolutioning storage architecture by transforming the fundamental approach to disk writes and unlocking unprecedented performance gains through sequential log design. The I by O or input by output bottleneck challenge here is the growing performance gap. While CPU speeds have increased exponentially over decades, disk access times have improved at a glacial pace. The widening gap creates a critical bottleneck where applications become disk bound, constrained by painfully slow random write operations. Traditional file systems exacerbate this problem with costly disk seeks and severely fragmented write patterns that waste precious bandwidth. Here, the core idea is all about write every text as sequential log. Here we discuss about sequential log structure, eliminate disk seekers, and pioneering innovation. First, when we talk about the sequential log structure, the sequential log structured file systems LFS write all data and metadata sequentially in a circular log pattern. It's fundamentally remaining storage architecture. And when we talk about these, eliminate disk seeks. This approach eliminates nearly all disk seeks during write operations, and it boosts the throughput dramatically and maximizing disk bandwidth utilization. And when we talk about the pioneering innovation, this was first proposed by Osterhart and Douglas in 1988, successfully implemented in Sprite OS by 1992 by proving that the concepts viability. So when we talk about how LFS works, here the segments and the log head. Here we have multiple points like segment division, memory buffering, sequential flush, and unified storage. First one, when we talk about the segment division, here the disk is divided into large segments, typically several megabytes each, creating manageable storage units for efficient organization. The second point here is memory buffering. Writing operations are buffered in memory segments, allowing the system to aggregate multiple writes before committing to disk. And the third point here is sequential flush. When memory segments fill, they are flushed sequentially to free disk space at the log head, maximizing write bandwidth. Fourth point here is unified storage. The log contains both file data and indexing metadata, so enabling efficient reads while maintaining write performance. And when we talk about the segment cleaner, here it is reclaiming space efficiently. So here it is the managing fragmentation. Over time, segments inevitably became fragmented with obsolete data version from file updates and deletions. So this fragmentation must be addressed to maintain performance. The segment cleaner intelligently combats live data from fragmented segments, consolidating it into contiguous blocks and freeing valuable space for new writes. So when we talk about the dramatic performance gains, here it is Sprite LFS prototype. Here we have here we talk about small file rates, disk bandwidth, and Unix systems. When you talk about the small file rates, here it outperforms traditional Unix file systems, and disk bandwidth utilization for write operations and unique Unix systems typical bandwidth usage. So the Sprite LFS prototype delivered groundbreaking results, matching or exceeding traditional Unix performance on reads and larger writes while revolutionizing small file write performance. This demonstrated that rethinking fundamental storage architecture could unlock previously unattainable performance levels. And when we talk about the benefits beyond speed, it's all about crash recovery and snapshots. Here we discuss about rapid crash recovery, natural versioning, and modern storage synergy. So when we talk about the rapid crash recovery, it recovery scans only the recent log tail rather than entire disk, dramatically speeding system restarts after failures and minimizing downtime. And when we talk about the natural versioning, multiple versions of files are naturally created by log structure, enabling powerful snapshot and time travel features without additional overhead. And we talk about the modern storage synergy. It's all about sequential write patterns that make LFS ideally suited for flash storage and RAID arrays, which particularly benefit from uh, avoiding random writes. The challenges and consideration here. Here we talk about read performance degradation, cleaning overhead, and memory cache dependencies. When we talk about the read performance degradation, it's all about file fragmentation on magnetic disks, which can degrade read performance over time as related data becomes scattered across the log. It requires careful management and optimizing strategies. And when we talk about the cleaning overhead, segment cleaning overhead must be carefully managed to avoid write amplification. When when cleaning operations themselves consume significant bandwidth and reduce net performance gains. And when we talk about cache cache dependencies, here the LFS assumes large memory caches to satisfy most read requests, making write performance an dominative factor. Systems with limited memory may not see full benefits. Modern impact and use cases. Log structures principles have evolved from academic research into production systems powering critical infrastructure worldwide. Their influence spans from mobile devices to data centers. Here we talk about flash file systems, enterprise storage, and write heavy workloads. So when you talk about the flash file systems, F2FS, JFF, S2, and UBIFS leverage log structure design to optimize flash storage performance and longevity by minimizing write amplification. When we talk about enterprise storage, NetApp's WFL uses log structured layouts for RAID efficiency, providing enterprise grade reliability with exceptional performance. When you talk about write heavy workloads, it is ideal for databases, its large size storage systems, and SSD based infrastructure where write performance is critical to overall system success. Transforming storage with log structure and design. Sequential speed advantage. Here, LFS transforms the disk write bottleneck into a sequential speed advantage, fundamentally solving one of computing's most persistent performance challenges. Order of magnitude gains by rethinking file system layout from first principles. LFS unlocks orders of magnitude performance improvements that were previously thought impossible. The future of storage. The future of high performance storage from mobile devices to cloud infrastructure depends on mastering and advancing log structure principles. Thank you.